Hello again, students. I hope you are very well and your family is all well and you're not going stir crazy and you're working hard on your online courses. We're going to continue with applications of the derivative. What we're going to look at is identifying maximum and minimum values of a function using our derivative. This is section 3.1. First, we need to get some terms straight. We say that a function has an absolute maximum on some domain D. So we have our domain, what x can be. We say it has an absolute maximum at a point C, x equal to C, not a point, but an x value. At x equal to C, we have a maximum, an absolute maximum, if f of c is greater than or equal to f of x for all x in the domain. Here's an example of a function with an absolute maximum. The absolute maximum value is f at c. No matter what other x we pick, f at that x is going to be lower than this. So this is an absolute maximum. This is going to be higher than anything else, any y value on the curve. But it's not only an absolute maximum, it's a local maximum too. Because if we think about values near C, like values over here, or values over here, if we identify some open interval around C, so we're talking about both sides, if we get close to C, no matter what x we pick, f at C is going to be bigger than that. So local maximum means we're just talking locally near C, in an open interval around C. That means C, we have to be able to approach it from the left and the right. So this is an example of an absolute maximum and a local maximum. Here's an example of an absolute maximum that's not a local maximum. Let's say we do this. I'm sorry. Here's an example of an absolute maximum. So at A, so f at A is a maximum, and it's an absolute maximum because this point, this y value, is bigger than any other y value on the whole domain. It's also a local maximum. Here, the function value at C is a local maximum because if we stay near C, around C, then f of c is always bigger than f of x. But it's not an absolute maximum. It's a local maximum, but not an absolute maximum. Let's go ahead and identify a minimum. F at b is a local minimum, because if we look near b, it's a local minimum because f at b is going to be less than any f of x for x near b. Okay? Notice that this function, if we're looking at the whole domain, if d is all real numbers, then this function doesn't have an absolute minimum. It has a local minimum, but no absolute minimum. Okay, let's look at what if our domain is limited. Let's say it looks like this. So our domain just extends from here to here. D is just extending from here to here. It doesn't exist outside those dotted lines. It only exists for everything between, let's call it A, and let's call this B. Okay. So, okay, so now let's look at what we can identify. Let's say this is A, let's say this is C, let's say this is D. These are the interesting points, right? These are the interesting places on the graph. Okay, so this one. We don't really like to call this a local maximum, because when we look at local minima or maxima, we want to look at an open interval around this point, this A value. And we can't because it's not defined out here. So it's like we can only approach it from one direction. So this is neither a local minimum nor a maximum. It's not an absolute maximum because this is higher, right? This is a local minimum, even though it's a point. And notice the derivative wouldn't exist there because the tangent line is vertical. And the tangent line, vertical tangent line has an undefined slope. So here, this would be a local minimum. It's not an absolute minimum because you have something lower there. This would be a local, F at D would be a local maximum and an absolute maximum because that's the highest y goes anywhere on the curve. F at B is going to be an absolute minimum. It's not going to be a local minimum because of how we said we have a local minimum or maximum when we can take all the values in an open interval around C. So it's got to be something, we've got to be able to approach this point from two sides. But this is an absolute minimum. Okay, one other example. And that is, what if we have something like this? Something that's, how about we do this? We have this weird function that, let's say, ends here and ends here, but it's not defined here. So it goes from A to B, but we have this value in here where it's not even defined. Well, it's not even, so we can't even talk about f of c. So we can't say there's a minimum or there's an absolute minimum or maximum there. But what if we define c so that we have an open dot here, but we have a filled in dot here? Well, in that case, f at c, oh, well, it's a local maximum and an absolute maximum. So that would work. It's a local maximum and an absolute maximum. What if instead of defining it like that, we defined it like this? Oh, wait a minute. Now, f at c, the y value is lower than anything around here. Oh my gosh, it's a local minimum. So when we have discontinuous functions, that kind of, you really have to think hard about what's going on there. And it doesn't work very well. So let's look at how we use this. We have two important theorems. The extreme value theorem, which says if f is continuous on an interval, if f is continuous on an interval AB, a closed interval AB, not an open interval, it has to be closed, then you can identify an absolute max and an absolute min. That works. If it's continuous, no holes on a closed interval, Fermat's theorem says if you have a local max or min, and at C, and f prime of C exists, so we don't have a case where we have some kind of cusp going like this. This is a relative minimum, this is a local minimum, but the derivative doesn't exist there because it's a vertical tangent. If a local maximum or min exists at C, and f prime at C exists, then f prime at C is 0. So what's going to happen is we're going to use these two theorems to identify places where we have, identify algebraically places where we have max or mins. Okay, so these are the two theorems. I need to also mention that a critical value of a function our values are x's so the critical values of a function, we usually describe them in terms of x, are the x values for which the derivative of the function is 0 or the derivative doesn't exist. We need these three things. We're going to apply these three principles, and we've seen them work out. If f is continuous on an interval, then we have some kind of smooth function like this, and it's a closed interval. We're going to have an absolute maximum and a minimum. Sometimes they're at the endpoints, or sometimes they're not at the endpoints, and you have something like this. But you do have an absolute max and an absolute min. Fermat's theorem, along with identifying critical values, are going to tell us for what x is we have local maxima and minima. So we're going to apply all this on some problems from chapter 3.1. And these are the problems I'm going to assign. But I'm going to do some of them. This is chapter 3.1, number 3, 4, 5, 6, 7, 9, 11, 13. Uh, 33, 35, 45 to 55 odd, and then 65. Bunch of problems to practice over the weekend. Again, I'm not so much interested. Yes, there's a way you could do this. You could get out a calculator or some software, Maple, Mathematica, MATLAB, graph each of these functions, instantly identify the local max and min, the absolute max and min. but I want you to experience it algebraically as well. So you can use your calculator to check yourself, I don't care. But you have to show algebraically what it has to do with the derivative, how you get the expression for the derivative, and that sort of thing. So I will be posting a few more videos with some of these problems on worked out on the video. I'll see you soon.